Saikon's going to take us home. He's going to talk about Storm, a framework for minimizing probabilistic programs to pinpoint errors.
Oh, thanks. Hi everyone, I'm Saikot. I'm going to talk about our work Storm, which is a program reduction framework for testing and debugging probabilistic programming systems. This is a joint work with Vincent, Zishin, and Sasha from UIUC. So probabilistic programming has been gaining a lot of popularity in the last decade. Probabilistic programming helps us makes it easier to describe statistical models of interest. They differ from standard programming language in three ways. First, it allows us to draw random values from distributions. For instance, for a variable x, we can draw samples from a normal distribution with a mean of 0 and variance of 1. You can also condition on observed events. For instance, you can observe that x is more than 0. And you can also issue several queries over the parameters. For instance, you can query for the posterior distribution of x. So if you look at the figure on the right, the line in blue is the initial distribution of x, and the line in green is the posterior distribution of x given the observation that x is more than 0. So probabilistic programming systems help us solve this kind of models using various inference algorithms, for instance, MCMC sampling or variational inference. So how do the systems work? So typically, a probabilistic programming system takes as input a program, which is a statistical model, a data which is input to that model, and certain inference parameters. And given that, it tries to infer the posterior distribution of the parameters in the model. In principle, what it does, it just applies Bayes' rule and computes the posterior distributions. But in reality, when things get more complicated, when these things need to work on real data in real world. So a typical probabilistic programming system can have multiple front ends, a compiler, its own API, different inference algorithms, and several underlying numerical libraries. So even though these programs are typically smaller than conventional programs, things can get pretty complicated, and even a 10-line probabilistic program can touch over 10,000 lines of code in these systems. So it gets very difficult to debug these kinds of systems. So let's look at an example from Stan, which is one of the most mature and popular probabilistic system. So this is from a bug report from Stan. This is the original model. This is the data that is input for the model. And you have certain inference parameters, which specifies that you have to run variational inference on this, and you have to run up to 1,000 iterations to reproduce this bug. So what happens when we give this as input to Stan? Unfortunately, it runs into this exception where it says that it encountered a NaN value during execution. So why does this happen? So there can be several reasons for this. So there can be some problem with the program itself. So it can be ill-specified for the problem at hand. Or there can be some erroneous value in the data itself which have not been accounted for. Or there can be some weird parameters which have some strange interactions with the code and data. Or perhaps there's a bug in Stan itself. Now, in order to understand why this happened, you need to understand what this program is doing, right? And doing that is non-trivial, even for the small-sized program. And you need to understand the domain information about this program and how it interacts with the data as well. So what if, instead of this, I give you the simpler test case which reproduces the same failure in Stan? So now, instead of the big model, you just have this simple model where you're just sampling from a digital distribution, and you have a smaller size data. And to reproduce this failure, you just have to run variational inference for 125 iterations. Now, in order to reason what this model should do, all you need to do is compute the posterior distribution of digital distribution. And to do that, you can easily refer to the PDF expression from Wikipedia. And you can use a simple calculator to do this. Now, if you plug in the values from the data, it seems like we can have a valid PDF equation. So in fact, it seems like there is nothing wrong with the model data here. And perhaps there is a bug in Stan. Actually, yes, the developers found the bug in the variational inference module in Stan in this case. So can we actually help developers simplify programs like this and make them easier to debug the systems? Yes. So we introduced Storm, which is the first program reducer for probabilistic programming systems. On a high level, it takes as input the program, data, and inference parameters, which exhibits some failure in the system, and produces a smaller version of that, which reproduces the exact same failure. Now, to do that, it applies a number of transformations on this input, and it combines the domain knowledge along with some techniques from program analysis to do that. So far, we have reduced over 47 bug debugging programs from Stan and Pyro, which are two popular probabilistic programming systems. So this is a brief overview of the architecture of Storm. So it has two main components, the translator, which translates for a program in the language of the probabilistic programming system to a Storm IR. And we have the reducer component, which has a transformer component, which applies transformations on the IR, and a checker component, which checks whether the failure can be reproduced. Apart from that, it also takes distribution specifications and order transformations and input as well. So in Storm, we have two main kinds of transformations. First is the basic transformations, which are common statement or expression level transformation that you could find in other conventional reduction tools like creduce for C. And you have some domain-specific transformations, which are called the probabilistic transformations, which use properties of distributions and the various functions to guide the reduction process. The checker module, it runs a transform program and monitors execution. It checks whether the failure can be reproduced by checking for the exact exception strings or timeout in case of infinite loops. And finally, in each round, it returns true if the same failure can be reproduced. Otherwise, it returns false. So evaluate a Storm on a number of RQs, and I'm going to touch upon the first two, and the rest can be found in the paper. So first, we try to evaluate how is the reduction quality when we apply Storm to all of these benchmarks. So we had three groups of benchmarks. First is the Stan issues, which are test cases obtained from the bug reports of Stan. Then we have Stan example models, which are some test cases we obtained from an open source repository. And then we have some test cases from Pyro. So we evaluated the reduction quality in a number of metrics. First is the code constructs, which is number of non-terminal language constructed in the parse tree. And we obtain up to 68% reduction in code constructs. We see a similar trend for lines of code, and we obtain up to 49% of reduction for Stan example models. The data reduction is highest in Pyro among the three cases. And for iterations, we found out you only need to run up to 10% of the iteration to reproduce the bug. So secondly, we try to evaluate whether the probabilistic transformations that we had are any useful. So here are the reduction scores for all the three different categories with the basic transformations. Compared to that, if we add the probabilistic transformation on top of that, we achieve a higher rate of reduction in all three scenarios. The reduction iterations is unique to Storm. So there are a number of things I did not touch upon, but you can find more about them in the paper. So in conclusion, presented Storm, which is a novel and automated framework for reduction for probabilistic programming systems. It combines techniques for program analysis with probabilistic semantic reasoning to guide the reduction process. And Storm achieves significant reduction in all three categories for Stan and Pyro. And the code is open source now. You can go ahead and play with it. So that's all for me. I can take questions now. Thank you.
How much does it help to reduce the iteration count? Because, like, if I think about probabilistic programming systems that I've worked on, like, the thing that really helps is making the program smaller. The data and the iteration count are much less significant. If you have a really simple program, then you can figure out what's wrong. But if you have a really complicated program, but it fails in 2 iterations, that's just like normal programming, and it's still hard.
So, the number of iterations you have to run to reproduce the failure directly translates to how long you need to run the program for. And this is especially significant in case where you're looking for some accuracy errors, right? So in that case, if you can just run for a smaller number of iterations to reproduce the bug, that should be enough, right?
Do you have a sense of what the relationship is between the number of errors that were due to a poor model or a bad model versus errors in the actual implementation of the programming system that you were using?
So in all the cases that we handled here, so the bugs were in the system itself and not the models. No, there are cases like that. But in this case, we just focus on the models which expose some bug in the system itself. So that's what we focus on.
Programs is